The next programming construct or building block that we are going to be working with is loops. And what loops allow you to do is something that computers like to do and we don't like to do as much, and that's repeat the same thing over and over and over and over and over. Because the computer is perfectly happy doing that, where people grow bored and tired repeating the same thing over and over. So your programs, you may have realized, are starting to get a little bit repetitive and carry on, where you start having to repeat a lot of the same lines of code or with very little variation. And that should be striking you as there's got to be a better way to do this. And that's what we're going to be learning about, is how we can do it so we don't have to keep repeating ourselves. So if I wanted to draw, say, I don't know, a bunch of boxes across the screen. I'm just going to comment these out for now. If I want to draw a bunch of boxes across the screen, what I can do is create a loop, and now I populated the screen with a bunch of rectangles. Now when we look at those rectangles, we'll see that they're all the same size, and they're all the same distance apart. And what my code is telling me is, in English, I'm saying while my while x is less than 600 minus w, I have a fill, and then I say draw a rectangle at while x, and then I make while x get a little bit bigger. Now this statement, as we look at it right here on my line 32, is the same as stating while x is equal to while x plus 25. These two lines of code are now doing the identical operation. While x is equal to while x plus 25, we do have a shorthand way of saying it where we say while x plus equals 25. In most programming languages, they're going to use that method instead of this method.
What instead of what?
The question was asked is, could I use something like this where I would say while x multiply equal minus 1 instead of while x is equal to while x times minus 1. So those two statements, again, are the same because the shorthand notation works with our standard for operations of add, subtract, multiply, and divide. So we can use it in all four cases if we want. So I could be using divide equal. I could be using a minus equal. They all are the same in terms of you're allowed to use them. So if you want to use the shorthand, I will encourage it. But if you like the longhand, that's okay too. And it's perfectly fine to keep using it. So what happens with this while loop is, a while loop is a great way to crash your computer.
Which is never a good thing, right?
Loop will run until that statement is true. So if I never made while x get any bigger, so if while x could never get bigger than 600 minus w, which in this case would be 580, so if while x could never get bigger than 580, my computer would run until it decides that it's out of memory. So that's kind of a bad thing. So if you've been on your computer and suddenly you get, where it just seems to lock up, not even a spinning, beach ball or a spinning clock or anything, it's just locked up. Chances are what's happened is it's gotten caught in a loop where it's trying to do something and it can't get out of that loop, and that is a high priority loop that's preventing it from doing anything else while it's running. So then it freezes up and crashes. Good in programming environments will recognize when it's caught in that loop, and it will go, whoa, I think we need to exit this now. And it gives you that option when it realizes it's been doing the same thing for too long a time. I'm feeling reckless right now, so I'm just going to comment that out and run it and see how quickly processing realizes it. I can see, and it's not doing anything. It's not crashing because this is a perfectly valid program. There's nothing that's wrong about this program. But it can't get out of this loop because it's never going to have while x bigger than 600 minus w, or 580. So now it's going to run forever. The nice part about processing, if you're stuck in a perma loop like this, you hit the stop button and it stops it, but it didn't crash. There are some times where it recognizes that it's working really hard on the same thing over and over, and it does say, hey, I think I better quit now. And then you say, yeah, good idea. So a while loop is going to run until that condition's met. The challenge on using while loops is we need to be absolutely certain that that condition will be met at some point, because no other line in my program was able to execute. So I'm going to allow it to run again. We'll see, I drew a big box right up at the top here. But notice that box happens after this loop. Now, if I can't exit the loop, it drew the first box, but it's now never left the loop. It's also now never going to get to that big box, which is after the loop. It's now permanently caught in this loop. I have no exit strategy. So this is a very bad thing to create in your program. Your loops must always have an exit strategy built in. The kind of loop we're looking at is the for loop. The for loop has slightly different syntax. When I look at a while loop is essentially, it's an if statement. It says, as long as this condition is going, so if while x is still less than 580, run the loop, run the loop, run the loop, and keep running until that's no longer true. A for loop, when a for loop runs, what we are doing is we are now specifying how many times I want this loop to run when I first create it. So in this case, I want this loop to run for 20 times. This will make 20 boxes on screen. So if we look at the result, I get these 20 boxes right here. Now these 20 boxes that show up, when we look at these, what we're saying is I'm creating what we can call as like a counter variable. This variable we use for keeping track of how many times we've gone through the loop. So while loops, we just say, while whatever condition is not happening yet, so until we meet that standard, just keep running in yourself. A for loop says, we're going to count each time we go through this loop. And each time we count through it, we're going to increase our counter. So in this case, my counter, by convention, usually we use the letter I for it. So I say int I, and I start counting from 0. Computers like to count from the number 0. We generally are taught to count from the number 1. So when you're going through school, it's always, we count to 10, we'd say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we ask a computer to count to 10, it will go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Because the computer likes to start with 0 as its beginning number. So we play into that. So we say int I is equal to 0, put in a semicolon. Then I is less than 20. That means I'm going to make 20 of these because the first time through I will have a value of 0. Then I is going to go up by 1. So we learned one version of shorthand today. We're going to learn one more version of shorthand. This next version of shorthand we say I plus plus. I plus plus, that would be the same as I is equal to I plus 1. So when we're making something go up by 1, we say plus plus. If we're making something go down by 1, we can say minus minus. So that's another shorthand that we can use in our numbering. So these are the same. So we say I is 0. And as long as I is less than 0, then each time through we'll make I get bigger than 1. Notice in the while loop, we actually had to type out in our code how we wanted something to go up in value. Now, if I look at this statement, it may seem a little bit confusing, where I say draw a rectangle at 4x plus I times 25 and 4y, then with width and height. 4x and 4y, let's see, they start out with values of 0 and 200. So when I look at this, that starts out at 0 plus I times 25. So what's that going to be the first time I go through my loop?
0.
What I am going to do is I am going to print out the value so that we can see this. Now, there's a cool feature built into processing where we can send text to the bottom of the screen or to what's called our console. So instead of making the text show up in our program, we can just send it to this bottom area down here. So the command for that is print line or print ln, and then inside the parentheses we put what we want to print. So in quotation marks I said 4x is, and then I want to add to that statement the variable 4x. So then we'll see what happens when I run this. And we'll see oh, 4x is still 0 because 4x never changes. We're just redrawing our box at a new value. So it should be 4x plus I times 25. And I'm not sure if it's going to be quite generous enough to do the computation there for me or not. It did. OK. Now if we look, we can see how 4x goes 0, 25, 50, 75, and goes all the way up until it hits 475. That's our 19 times or 20 times through, since the first one is 0. And then it resets and it starts back at 0 the next time the whole program runs itself. So we're able to see how that number goes up each time. The final part on loops is where we put a loop inside of a loop. Now, if you look at the code that's highlighted, what you will probably realize is there's a lot of punctuation, there's a lot of parentheses, semicolons, curly braces, and on first glance it looks really complicated. But if we study it a little bit further and look at what's actually happening with it, it doesn't have to be as overwhelming. But when you first look at it, it's like, oh my gosh, what is all of that stuff? And that's way too much. It looks like real programming. And we're a bunch of designers here, and we don't always want to do that. That's okay. So if I look, that little chunk of code creates a 5 by 10 box on screen. And we can see the 5 by 10 box right here on screen. It's the blue box. It's the grid. So what it does is we're going to loop through and create a row. And then we will draw the columns within that row. So it's going to loop through, and we say create a row, then we draw the 1, 2, 3, 4, 5 columns. And then we're going to move down and draw the next row, and it's 5 columns. Because if you realize we have 10 rows, 5 columns. Now, this method of drawing a grid is pretty much what your computer is doing when you look at your screen. It's starting in the top left corner and drawing that first pixel on your monitor. And then it works its way across the screen. So it starts in the top left and it works its way across one pixel at a time, goes down a row, draws the next line of pixels. Goes down a row, draws the next line of pixels. Goes down a row and draws the next line of pixels. So it keeps doing that. That's how your computer draws it on screen. So learning to understand that this is how an image file is constructed. An image file is a pixel grid. Smaller dots than these blue squares, but it's just a grid of squares. So that's all an image is. And if you understand that, suddenly it becomes possible to start manipulating that, because you realize, well, if I bring in a 100 by 100 image, I can now use a for loop to cycle through each one of the pixels in that image and transform it and modify it or do something to it. And that's really powerful. And if we think about it, that just processing an image may not be what we're after, but maybe we want to process the image from a webcam. So if there's a camera on the device, so if like your computer displays have a built-in camera on them, so you could be gathering that input, processing it one pixel at a time, and then giving us a different output. Don't just give us the standard video, but instead manipulate those pixels. Or sometimes we can do edge detection. So we can analyze that image so you can actually have your feed from that video camera, and we can be live making animated particles or snowflakes or other things interacting with that image on screen. And the cool part is a lot of the complex libraries for how do we access the camera, how do we cycle through all the pixels, that's already been built, and we just need to figure out what we want to do with that information. And these are some of the things that we'll be looking at towards the end of the semester when we're doing more advanced topics. And you can peek ahead in your book and see some examples of it and go, ooh, that's kind of cool. But for right now, we're just going to draw a basic grid. So we have the rows and we have the columns. Now each time we are drawing it, each one of the squares is going to be 10 pixels wide, 10 pixels tall, and then they get positioned based on an offset. So each time we need to move them over 10, that's how we draw the grid. If you start each time, if you're like, okay, I'm not sure how this loop generates the numbers, write out on a piece of paper what those values are each time we go through the loop. And remember, it's a loop inside of a loop. So we have the outer loop that happens once, where j starts out at 0, and k starts at 0 in the inner loop the first time. The next time through, k is 1. Then it's then k will be 2, then 3, then 4. And then once k is greater than 4, meaning it's now equal to 5, it's time to bump up j to that next point, and then we're now on row 2. So we figure out with j and k how they change, and we use that to our advantage to draw our elements on screen. Then we can cheat and manipulate that system and create a flag. Now, those aren't stars in the flag, but instead are squares. I do have a modified version that I couldn't find. The last time I did this, I got grief from the class that they were squares and not stars. So I had to go back and remodify them to stars, but I don't know where that file landed at the moment. So functions are probably one of the more powerful components of programming. A function allows you to take a set of instructions and encapsulate it so that it's easier to reference it or to reuse it. Every function that's built into the language, someone else has programmed a function, so you can just type one line of one code or one line of one command and say, do this, and it doesn't. So when you say fill and you specify a color, someone else had to write the instructions to tell the computer what to do when you say fill. And if you give it one parameter and you say fill 255, then it has to know, oh, if there's only one thing, we're filling it with ranges of black and white. If you give it 2, it's black and white with transparency. If you give it 3, that means you're specifying an RGB color value. And then if you put in a hex value, how to process that differently. So all of these things, someone else has already written out the instructions, so you have the convenience of just typing in the word fill and listing whatever color you want. So you've been using functions. You just haven't been creating them, except with your draw and setup. Draw and setup are the two functions that are built in the language that you already use. The other ones are pre-programmed, and today we're going to start making our own functions. So if I run this sketch, got bouncing ball. It's not very exciting, but it's a bouncing ball. Now if I look at my code that I've been provided, what we will see is I've indicated 4 functions that as your programs get more complex, your draw function is only going to reference other functions instead of have actual instructions within it. So right now I have background as an instruction, fill, ellipse, and then I change my speed Y, then I find out if I've hit the boundaries and modify it. Well, that's okay. But instead, what we want to think about doing is, instead of saying background right there, is if I type in the word void, clear background, and then put in all my curlies, I can now put in that instruction, comment that out. We're not going to use that up there anymore. And now I'll just call the function that I made. So I made a function. Now we'll get into this whole void thing in a little bit and talk about that. Doesn't matter right now. And the common sense side of you should be saying, wait a second, we had one line of perfectly functioning code and just replaced it by 3 other lines. How's that saving me any time or effort? But what it's going to do is it's going to give you a much better organization to your code, more than just throwing in extra comments will do. And it encapsulates your code. And that encapsulation means we're now starting to make our code a little bit more portable and self-sustaining, so that we can actually start to use it in another program. So I could make a code library, and then I can now just reference it by attaching that library, which has a bunch of functions, helper functions, and then I stick that in a project folder, and now I just type in the name of the thing I want to use. I don't have to copy in all of those lines of instructions. Now, my background, clearing it, background 128, well, that's not very exciting. But if we, instead of doing that, but we do the trails one, where I say fill 128, 100, and then rect 0, 0, width. So if I use the ghosting method instead, okay. So it's a 2-line thing, and I could add both of those lines up there. But if I look at it now, and I'm going to even just get rid of these commented lines just so it's cleaner to look at. When I look at my draw function, it says clear the background. That's really readable. Having the instructions of fill 128, 100, reg 00 width height, that's not as immediately readable or recognizable as to what's happening. So when we start thinking about how this organizes our coding, by taking a set of instructions that represent one single activity or task, in this case, wiping the background, and putting them into a function and then just calling that function, that makes the rest of my code much more human readable. The computer doesn't care that we've done this. The computer probably is saying, silly human, you're adding in extra lines. Why do you need that? But we as people, when we look at it, we want something that's easier to see and digest. Because if my instructions, which I had clear background on there, get rid of that. So if that's all I see inside my draw function, let me just get rid of that. Clear the background. Update objects on my screen. Check to see if those objects have hit the boundaries, and then render or display them on my canvas. So when I look at it this way, suddenly my program is much easier to see and understand. I just have to figure out what those other lines are going to be. I'm going to fill in a few lines of code and then take a pause and allow you to try to populate it correctly to see if you can get it working. The draw thing at the bottom, we'll get into that and what that means in just a little bit. So that that's now referencing something that's talked about in the text, and it's the next part of working with a function, and we'll understand that shortly. We had the first function, clear background. Now I have the next three stubbed out: update, check boundaries, and display. Your task is to then take the lines of code that were previously in draw and put each one into the correct function. Reference these new functions inside your draw, hit run, and see it perform flawlessly. At these commented lines of code, they are doing a couple of different things. I'm going to add in some extra returns to separate them out, so we can see that these two lines of code speak to setting a fill color and drawing an ellipse. So that's our thing that we are trying to display. So I'm going to cut that out of here and go under display and paste that in and turn off comment. Now if I'm updating my object, that's really here. I'm taking the y of the object and I'm updating it by speed. So go paste that in, and then that just leaves me checking boundaries. I'm finding out, has y got less than 0 or is y greater than 400? Or that's checking my boundaries, my margins. I'll edit, auto format, Command T to make the whole thing pretty. And now we can see I have changed my program so that it's now set up in a little more kind of straightforward method. If I run it, it runs the same as before. Quite a few more lines of code than we had in it originally, but one, it's better organized, and two, it's going to become much more useful as we move into working with objects. Because when we are working with objects, we're then able to set up these items for each individual object. So if I want 10 copies of something moving on screen, I don't want to have to create 10 check boundary functions. I want 10 update functions and 10 display functions. And, well, we only clear the background once, but still, that's a whole lot of functions for 10 objects. It's doable. I set the assignment to add 100 objects on screen, and a student decided to prove that you didn't have to use classes or objects to do it, but instead hand-coded all 100 objects on screen. So when you're faced with the same homework assignment, it's now 1,000 objects, because nobody's willing to put in the time to hand-code in 1,000 objects. And if you are, well, that's defeating the purpose. So learning how to use these for individual objects is now going to allow us to construct new objects on screen and be able to work with them with much greater flexibility than we can at the moment. Because right now we're limited to everything we want on screen. We have to code it from scratch with all of its unique values, even if the objects are virtual identical copies of each other. So if I had 1,000 snowflakes falling down, I would have to hand code in all 1,000 snowflakes, and that just wouldn't be fun. When we're working with objects, the programming construct that we work with is called a class. A class allows us to take a set of instructions and put it into a self-contained element. The cool part about using classes is once we have the class, that's essentially our template. And then we can make as many objects from that class as we want when we work with our program. When creating a class file, we will sometimes append the class to an existing document, and sometimes we will add the class to our project as a separate file. There's good and bad about doing both. The good is when it's a separate file is that your file is shorter, so it's easier to scroll through it. The bad part is you have to then go between different tabs to see said file. So it's good and bad. So I'm going to make a new tab. And when I make a new tab, it's going to ask me to come up with a name for the file. The name for the file that I am going to use here for the demonstration that we're doing in class, I'm going to use a ball. But if you want to start imagining you're doing something bigger and better and more impressive, like a cow, you could certainly do that. Or a laser beam or whatever makes you happy. Conventions when we are using classes. Classes are named with a capital letter. So if I want to make this ball, I will type in ball, capital B, A-L-L. And now if I hit OK, we'll see we get this extra tab that showed up here. And now if I look inside my folder, the same folder you downloaded with loops and functions, there is my functions folder, and inside of that is now a file called ball. So now I have that new file. Now we're going to make this a class. We're going to start out, and the ball is going to have a random size, a random fill color. It's going to start out at a random place on screen, and it will have its own unique speeds. So every time we create a new ball, it's going to just show up somewhere. Because we can. And because we can, this is one of those times in life when we should. So the syntax for creating a class is I start out with the word class. And then I type in the name. In this case, it will be ball. And then I do a curly brace. Now always hit your extra return and closing curly brace before you continue on to make sure then you're going to be in good shape. Now, a couple of things that need to happen when we are creating a class. One of those is that we set up all of the variables or parameters that are unique to that object. So I'm just going to make a comment for variables. We'll go put some in a moment. Then we will need a constructor function. And then we're going to need a couple other functions. And well, this ball, the cool part about this ball is that this ball is going to look very much like the ball that was in my function here, where it has an update. It's going to check its boundaries, and it will have a display method. So it's going to end up using those three items as part of its kind of ball behaviors. So we're going to be able to work with that. So we will have then our methods. Functions that are inside a class are referred to as methods. Now my ball has a float x, float y, float width, float height, and finally a float color. Not float color. Color C. Sorry, my bad. So we have variable types. We had ints, we have floats, we have strings, we had booleans. Now another type we can refer to is color. Now in my constructor, say ball, a couple parentheses there, return twice, a curly brace, we get our curly braces. Now when I reference the ball class, that name needs to match the name up here and the name of the file. So the file name, the class name, and the constructor name are all the same. That's very important. So we can say x is equal to random, say 1, don't know how big this was, 6 by 4. We'll start them out on screen 100n. Y is equal to random. Now when using random, we provide the range of values we want. So this will give me a number between 100 and 500. Gives me from 100 up to, but not including 500. Up from 100 up to, but not including 200 on the next line. So it gives me those values. Now if I set my width is equal to random 5. Well, if I want them to be balls, I probably should just use one value for width and height and shouldn't have two random. If I want them to be variations of ellipses, then I could randomize it. But I'm going to let them be balls, so I'll just use W for both values on my ellipse. I did forget, besides color, we'll also need a float speed X and float speed Y, because it's a moving object. Now the way we can specify our color, C is equal to color, random 255, comma, random 255, comma, random 255. When we specify a color, we say color, C is equal to color, and in parentheses we say the three values, the RGB components. In this case, it'll be random numbers, so every one of these balls will be a new color. That works. Now, if they're going to have different speeds, speed x is equal to random 3, 6. Speed y is equal to random 3, 6. So the request was, how do we make these multitude of objects all moving and being the same but different? And that's really what this is bringing out, is constructing the ball. Each ball will have a random location, random size, random color, and random speeds. Now that we have that, it becomes a matter of, okay, now it's time to figure out how to add in some of the other parts to it. The methods that our ball is going to need is, the ball is going to need an update, boundary check, and display, because each ball will hit the boundaries at different times. Each ball will update and display with its own values. So I copied those methods from the previous, from my functions file. Command T to line it up. And then add in the speed X options. Copy pasting while you are coding can be a speedy way to move things around. You just have to be really careful you don't flip-flop things or make a mess out of it. Now that I've cleaned out a lot of the old code here, I'm going to create a new object, and I'll call it ball B. I'm going to call it B0 for now, because then we'll have a ball 1 and a 2 and a 3, and we'll add a few of them in there, and we'll see how that works. B0 is equal to, oh no, sorry, B0. Then B0 is equal to new capital B ball, throw in some parentheses. Now, the cool part is B0 has a method called update. B0 has a method called check boundaries. B0 has a method called display. So B0 is now able to show up on screen. Oh, except that I forgot to modify the update to match double W. Let's try again. There we go. So not that exciting yet. But if you had a B1, B2. Oh, and I forgot to change the display to utilize our random things as well. Fill with a random color. That should do it. Right. B2, we might as well add in ball 3 as well.
What was void display on the ball one?
One sec. We fill with our random color instead of filling with red. I now have 4 cows.
Can you put those in a for loop to randomly generate X amount of balls?
Can. But we then have to have a method to keep track of them. And I'm not, looking at the time, I'm not going to go into that today. So if we look at what the code did, before we drew one ball and put its behavior into a bunch of functions. But if I take that ball and turn it into its own entity, so the ball is kind of in charge of itself. The ball has a constructor, so it takes care of where and what it's going to do. It has its own methods that keeps track of itself. Then my main program just tells that object to, why don't you update yourself, check your boundaries, and display yourself on screen. Now, you could make an argument that the ball you could just call one function that would call all of those functions for that ball.